right? The spring up against the wall, it's just sitting there, nothing's happening. But as soon as you push in on the spring, you kind of compress the spring, you can feel it. It's pushing back on you, right?
Yeah.
And we can calculate the magnitude of that force that's pushing back on you. And it's a really small equation, right? It's F equals kx. You'll see a negative there a lot of the times, but a lot of the times negative just refers to direction. So I just like thinking of it as F equals kx, where k represents, it's like the spring coefficient, which is kind of like how hard is it to compress. That's what k represents. Like, so you can imagine like a spring on a car, really hard to compress, whereas like a spring, like a Slinky spring.
A Slinky, yeah.
Yeah, a Slinky spring is super easy to compress. So very low k coefficient. And x represents from the kind of neutral position, what distance, it's a meters, what distance have you compressed it, right? And so that's where F equals kx is the the spring force equation. If you want to calculate the spring force, you multiply the k by x. They will give you k. You don't need to memorize any k constants when it comes to springs, at least.
Yeah.
And yeah, so that the spring force is another one. And also when you have like elastic bands are another example of like the spring force, where when you pull on an elastic band, you can feel the force. Exact same idea. The application is a little bit tougher, so normally you'll see it just with the classical springs, but that's another application of spring force.